All right, so here we all, nice and subdued on this Monday that we probably wish was over hours ago. Actually, I kind of wish it was over ever since this morning, so before even getting up. Yeah, well, two of us are not good enough shape to even be here today, so well, Nikesh and Vivian are, yeah, yeah. So, and Vivian put an appearance, but then didn't want to stick it out. So, and I'm envious. So, okay. So basically, we're just going to see how much I feel like covering today, and whether or not I want to call on anybody. If I don't feel like, what?
I said
Okay. Well, I guess some of us are readier than others. So, yeah, I mean, technically I'm still behind, but I think what I absolutely have to cover today may not be all that much. Again, we'll just see how this goes. But yeah, it's kind of sad that we're only about a third of the way into the semester.
And we all
Why would you
feel like
say
this,
that?
I know.
I'm sitting here just like, the semester's like halfway over. It's like done now.
It's
You
not.
know, whatever. And now it's only a
Yeah.
third in my mind. I hate you.
That escalated really quickly.
She tells me that every week.
Yeah.
Okay. No, got it.
Yeah.
And yeah, of course, I mean, yeah, Stanford, they're in quarters. They just started classes today. So they're all bright and bushy-tailed, like ass. So, okay. Oops. I seem to be missing a page. Oh, okay. Never
We're on
mind.
3.5,
I'm not.
right?
Yeah, I guess there's a tiny 3.4. So, because last time we were looking at Newton-Cotes Rules. And all that means is you choose the nodes x1, x2, xn to be equally spaced. Within AB. And there's variations. You could choose them to be open or closed. So open rules do not contain the endpoints A and B themselves, and closed rules do. So the weights, well, weights as always, are the integrals of the Lagrange polynomials for those points. And this is not just Newton-Cotes, this is any interpolatory quadrature rule. And what we saw three simple Newton-Cotes rules: midpoint, trapezoidal, Simpsons, that all use an increasing number of nodes, and we saw that the degree would increase, because I think the degree of these rules are either n-1 or n. So I think for higher degree of accuracy, and you just go ahead and use more nodes, because what you're doing is you're fitting your integrand of a higher degree polynomial. It's going to agree with that. Your polynomial will agree with that function at more points, and your rule will be able to integrate more polynomials exactly. And the answer is no. It doesn't work that way. And the reason why is as the number of nodes, n, increases, you can get weights that are negative. You think of any quadrature rule as being like a Riemann, actually not like, it really is a Riemann sum. You're summing the areas of rectangles. It seems kind of odd to have a rectangle with a negative weight. So one thing that pretty much any textbook in this subject will say is um, for n greater than or equal to 11, so degree of accuracy of at least 10, you will always get at least one negative weight. Okay. But I've actually found that I guess maybe it depends on whether a rule is open or closed. I think what I just experimented with generating closed Newton-Cotes rules just for higher and higher degree, and I think the first time I hit a negative weight was around n equals 8 or 9, and then it went positive again for one more value of n, and then it stayed negative after that point. If you use open rules, maybe threshold is a little higher. Maybe that's why the textbooks always say n greater or equal to 11. When I found it kicks in even earlier than that. When you have negative weights, that makes the quadrature rule numerically unstable, and in fact, a consequence of that is as n goes to infinity, the error, which is just your exact value minus what you get from your quadrature rule, does not necessarily go to 0. So you don't have a guarantee that the error is actually going to, that the quadrature rule, as using infinite number of nodes, is actually going to converge to the exact integral, which flies in the face of what you've learned about from a definition of an integral, Riemann sums. If you use a valid Riemann sum, like n rectangles, and the number of rectangles go to infinity, of course it converges because that's the definition of the integral. But those Riemann sums, by definition, have positive weights. So if you can guarantee that whatever quadrature rules you're using, if you define them as in terms of the number of nodes n, that the weights will always be positive, then yes, the error does go to 0. But for Newton-Cotes, not happening. And in fact, this is related to something I talked about with interpolation. Runge's example, with a 1 over 1 plus x squared, or minus 5 to 5. So in that case, we looked at the polynomial interpolant of degree 10, using 11 points, all the integers from minus 5 to 5. And that polynomial interpolant was awful. It was way off. So then when we, so then if you use that same polynomial interpolant, you integrate that to approximate the integral of 1 over 1 plus x squared, you could expect to be way off also. So these interpolatory quadrature rules will only be as good as the polynomial interpolant. So if you use equally spaced points in high degree, that's bad for interpolation, and it's bad for integration too. Whereas if you use the one alternative, and so that's the thing I really spent time on, but it's worth mentioning. A certain approach to integration called Clenshaw-Curtis quadrature. And what that does is, instead of using equally spaced points, it uses the Chebyshev points as your nodes. So in other words, it'll either use the roots or the extrema of the Chebyshev polynomials. And those have unequal distribution, that they are clustered around the boundary. So that works quite well. In fact, later we'll see Gaussian quadrature, which people generally think of as the best. And one of the reasons is it's guaranteed to have positive weights. But, as some of you proved in 685. it's been shown in certain cases, Crenshaw-Curtis, even though it has a lower degree of accuracy, can actually be better than Gaussian. And again, not something I'll spend time on, but it's good to be aware of these Crenshaw-Curtis rules because of how good they are. Okay. All right. So using higher degree Newton-Cotes rules is not a good idea. So what we're going to do instead is use a different approach where we take the lower degree Newton-Cotes rules, like from last time, midpoint, systems, trapezoidal, and instead of using them on the whole of the interval AB, we'll use them on subintervals. And that leads to one of the most commonly used, most straightforward approaches to effective numerical integration. And these are called composite rules. So what you do is, in a composite rule, that you divide the interval AB into n subintervals with h, which is b minus a over n. So generally use equal width. And you apply some sort of interpolatory quadrature rule, like a Newton-Cotes rule, on each subinterval. Okay. Now, when we looked at the error of a Newton-Cotes rule, we saw that the error was always proportional to some power of b minus a cubed, b minus a to the fifth. And I pointed out that what if the interval AB is large? Then that part of the error could be enormous. So this gets around that problem because we can choose a large enough number of subintervals so that h is small. And what we'll see when we look at the error, we'll make the error the error will turn out to be proportional to a power of h, so something small rather than something large. Okay. Now, I'm going to list three composite rules to go with the three Newton-Cotes rules I covered last time. In each case, we're going to divide into n subintervals. Although the way we apply these rules, it's not necessarily a one-to-one thing. Applying Simpsons or midpoint rule on each subinterval. Sometimes it could be like a pair of subintervals or something like that. But you'll see when I describe these. So the most straightforward one is the composite trapezoidal rule. And in calculus textbooks, this is what they teach, but they never include composite because they don't talk about the basic rule. So, in other words, every calculus textbook manages to offend me that way. So what we do is we apply. I'll show you how we divide the intervals. So x naught is a, xn is b, and then we have these subintervals. Each one with h. Okay. So, if we apply the trapezoidal rule on this subinterval, well, the width of the subinterval is h, so we take the width of that interval, so it'll be h over 2 f of the left endpoint, x0, plus f of x1. So this is a trapezoid for the first subinterval. And then we move on to the next. So it'll be h over 2 f of x1 plus f of x2. And then we keep going through all the subintervals till we get to the very last one. So f of x n minus 1 plus f of x n. Okay. So this shows where the composite trapezoidal rule comes from in terms of the basic trapezoidal rule. We just apply the basic rule on each subinterval, so it's a one-to-one association. But now we should simplify this. And notice we have f of x1 shared between two trapezoids. In fact, all of the interior points, x1, x2, and so forth, belong to two trapezoids. So we can combine, or I guess it's one of your students said, Abby, gather like terms.
Yeah,
Yeah. So we'll have h over 2 on the outside, because that multiplies everything. F of x0 plus 2f of x1 plus 2f of x2, and so forth, down to 2f of xn minus 1 plus f of xn. So we have h over 2 outside. On the inside, the endpoints have a coefficient of 1. All others have a coefficient of 2. So that is the composite trapezoidal rule. Now, if a function happened to be periodic, then f of x0 and f of xn would be the same. So then we'd have n terms in here, all the coefficient of 2. In fact, the trapezoidal rule, as I'll prove later, I don't know if it'll be today or maybe Wednesday, is actually the most effective for periodic functions, where the period fits into the interval AB. Otherwise, it's not so great, really, but at least it's simple to implement. Okay. I'll get to an error formula later, but first I want to I'll show you the other two best known composite rules that are based on Newton-Cotes rules. Next is the composite midpoint rule. What that does is you apply the basic rule on each pair of subintervals. So your same setup in terms of your points. So what happens is you apply the midpoint rule first on this pair. So your integral so applying the midpoint rule to this, all your subintervals still have width h, even if they're badly drawn. So the width of this whole interval is going to be 2h. And then your midpoint, in this case, would be f of x1. and then 2h f of x3 is the midpoint of the next, and so forth, all the way down to the very last one, 2h f of xn minus 1. So in fact, many points you're not actually using, and we also require that n is even. So I want to point out that the Trapezoidal Rule used n plus 1 function evaluations, evaluate f at every point from x0 to xn, whereas in this case, we have n over 2 evaluations of f of x. Okay. As opposed to, and I'll fill this in, n plus 1 evaluations. Okay. Now, what I could do is write this in a way that uses, still performs on the order of n function evaluations. So that would be h, and then f of x a half plus f of x 3 halves and so forth. I'm going to have x n minus a half. Where xi, integer or not, is a plus ih. So this first point would be a plus h over 2. This next point would be a plus 3h over 2, and so forth. And this one would be b minus h over 2. So at least here we have n evaluations. So I'm writing it this way so as to be to help compare to the composite trapezoidal rule, because this written this way is doing about the same amount of work. N evaluations of f of x versus n plus 1. Okay. So what happens is pretty much all of the f values are being multiplied by h in both rules, pretty much. The only difference with composite trapezoidal rule is that you're using different points, and you're also making use of the endpoints a and b, whereas here you're not. But it's important to have the amount of work be the same so that when you come up with an error formula, you can compare the error and see which one is more accurate. Okay. All right. So the last one is Composite Simpsons rule. So you assume again, like the midpoint rule, that n is even, and you apply the basic Simpsons rule from last time on each pair of subintervals. All right. So same setup. So if you apply the basic Simpsons rule on the first pair of subintervals, then, so it's the width of this, 2h, divided by 6 times f of x naught plus 4, f of x1 plus f of x2, and it covers this part. And then you move to the next. So you're applying Simpsons rule on an interval of width 2h. So just filling in what the basic rule is from last time gives you 2h over 6 f of x2 plus 4 f of x3 plus f of x4. Notice that f of x2 is shared between two instances of the basic Simpsons rule. And you keep going until the last pair of subintervals. So f of x n minus 2 plus 4 f of x n minus 1 plus f of x n. Okay, so now we can do the same thing as in the composite trapezoidal rule and combine all of these. So we have h over 3, and then f of x naught plus 4 f of x1, and then because f of x2 is shared between two instances of the basic rule, we combine those like terms, and we get 2 f of x2, and then 4 f of x3 plus 2 f of x4. So notice the pattern of the coefficients. 1 for the endpoint, and then 4, 2, 4, 2, and so forth. It keeps alternating between 4 and 2 down to the end. So we have like 2 f of x n minus 2 plus 4 f of x n minus 1 plus f of x n. Okay, and that's it. So, so we're using the same points to plug into f as composite trapezoidal rule did, but the coefficients are different. So with trapezoidal rule, you had h over 2 out front, and you had 1, 2, 2, 2, 2, 2, 1. And then in Simpsons rule, you had h over 3, and you had 1, 4, 2, 4, 2, etc., 2, 4, 1. So the weights are very different. Yet the goal of achieving more accuracy, which generally it does, because it's using a higher degree interval in the quadratic instead of a linear. Okay, so those are the three most often used composite rules that are based on Newton-Cotes rules. And certainly the sort of thing that's relatively easy to implement in MATLAB. Because these points, these xi's, since they're equally spaced, very convenient to work with. Just form a vector of x values, you can plug them into f, and then have some sort of loop that multiplies them by the appropriate weights and adds everything up. All right, but now it's time to talk about error. How accurate are these? And we can use the error formulas we got from the basic rules. Basically, we're adding up those errors over all the subintervals. So for the trapezoidal rule, that the error in the basic trapezoidal rule turned out to be minus f double prime at some unknown point over 12 times b minus a cubed. So what are we doing now, though? Now we're applying trapezoidal rule n times on subintervals. Each one has width h. So that plays a role of our a and b this time. It's going to be xi minus 1 and xi. So for a composite rule, so the error is going to be a sum of from I equals 1 to n, because we're using the rule n times, times the error on the interval xi minus 1 to xi. Okay. So now we can just go ahead and, so this is your A and this is your B. So we can fill that in here. So that's going to be, I'll factor what up, well, I'll factor it out later. So we have minus f double prime of some unknown point, I'll call that a to I, over 12. And then the width of each subinterval is h, so I'm going to have h cubed. And each unknown point belongs to its respective subinterval. So now what I'm going to do is I'm going to make it, first I need an assumption. I'm going to assume that f double prime is continuous on AB. So what I'm going to do is I'm going to multiply and divide by n. And now I'll factor out what I can. So I have minus h cubed n over 12. And then I have 1 over n times the sum of all of these values of f double prime at these unknown points. Okay.
Is this the composite rule for all three, or just the trapezoid?
What I'm doing now is just trapezoid. Yeah. So, and a similar approach can be used for the others. Okay. All right.
That's negative h cubed n. Is that right?
Yes.
Okay.
Right.
Sure.
Okay. Now, recall how we define h. H is equal to b minus a over n. So that would mean that hn is equal to b minus a. So I can absorb one of those h's, combine it with the n to get me a factor of b minus a, and then I still have an h squared left over. So now I have minus b minus a h squared over 12. And in here, I have the average of all of these values of f double prime all lying within AB. And it turns out what I can do is replace them by a single instance of f double prime at some unknown point, eta, in AB. And the reason why I'm allowed to do that is, okay, so the average if you take any function f of x, okay, so if f is continuous on an interval ab, and all these points xi are ab, so now I'm making a more general statement because it's one of those good to know things. You can say the average value of f at these points, chosen within AB, is equal to some value f of c, where point c is also in AB, by the intermediate value theorem. And the reason why is simply that the average of these function values, just by the nature of averages, has to be somewhere between the minimum and the maximum values chosen from here. So because f is continuous, f has to assume all values intermediate to those max and min, and that would include the average. So an average of function values, when a function is continuous, can always be replaced by f at some unknown point in between them. And that greatly simplifies these error formulas. So now we're done. This is the error formula for the composite trapezoidal rule. Any questions about how that was done? All right. Now, I won't go through it again, but the process will be very much the same. If you take the error formulas for basic midpoint rule and basic Simpsons rule, sum them up, in this case over like n over 2 instances for Simpsons rule.
Excuse me, I have a question.
Yeah.
Is there any way how to find C?
No. There's no, because basically what you'd be doing is, okay, once you compute this, you want to solve f of x equals this. That's like solving nonlinear equations, like from chapter 1. So, yeah, there's no easy way to do it. And for error analysis, generally you don't care. Because, at least because you know it's equal to this, if you can come up with a bound on f double prime over the whole interval, then it gives you a bound on the error. And that's how these theorems, like intermediate value theorem or mean value theorem, that deal with unknown points, that's how they generally work. That we know that the error involves some function evaluated at some point within a known interval, and we can use that to at least bound the error, because the error itself is unknowable anyway. But if we can at least get a handle on how big it can get, then that's useful. And the funny thing is, in Calculus 1, where the intermediate value theorem and mean value theorem are taught, they always give problems related to them, saying, find the unknown point. We're not supposed to care. At this level, no one cares. But they got to give some problem involving these theorems, so they just give that. And it's stupid, but whatever.
Okay, right before you box the error formula, the line, right before that, okay, so we have h cubed n over 12, right? Negative h cubed n over 12
Yeah,
times 1 over n.
yeah.
Okay, so the n's cancel.
Well, no, I'm using them for different purposes.
Okay,
Yeah,
that
so
makes sense.
n h becomes b minus a.
Right.
The other n is used here.
Okay, I
Yeah.
couldn't figure out where the
Yeah.
lower n, the denominator n was going.
Ah, okay.
Okay,
All right. Yeah, so everything in parentheses got absorbed into.
becomes that,
Yeah,
got
yeah.
it, okay.
Okay. Now, just been asked, this comes from Dr. Coates at graduate school, for departments to nominate someone for the Graduate Student Hall of Fame.
Wow. That's a big typo.
Yeah. Well, I'll have to think about that. Okay. not sure what the criteria is, but all right. So, so what about the other rules that we've seen? So we have composite midpoint. And this is for, I wrote it out twice. This is from a second form that uses n function evaluations. So the error is equal to f double prime, an unknown point again, over 24 b minus a h squared. So in both cases, the error is proportional to h squared. We have the second derivative, we have b minus a, but the constant is different. The constant is half as much. So composite midpoint is generally a little more accurate than trapezoidal. But the amount of work is about the same. N evaluations in this case, n plus 1 in that case. And then finally, Composite Simpsons. Well, the basic rule had error about proportional to b minus a to the fifth. So what we get is dang it. So minus fourth derivative, unknown point, over 180 times b minus a h to the fourth. Okay. So let's talk about these powers of h. Those are very important. So here, as our trapezoidal rule, is h squared. So we say these rules are second order accurate, whereas Simpson's rule is fourth order. So what that means, not always, but generally, if you reduce h by a certain factor, then the error will be reduced by that factor raised to that power. So for instance, if I cut h by a factor of 10, then in composite midpoint trapezoidal rules, the error should decrease by a factor of 10 squared, or 100. Whereas if I do the same thing with Simpson's rule, the error should decrease by a factor of 10,000. Now, like I said, it doesn't always work out that way, but usually does. What can throw things off are the derivatives. And actually, a really good example to see when these error formulas work as expected and when they don't. So a couple functions I can give as an example. Oh God, what does Dr. Schroeder want now? Okay, I shouldn't have said it on YouTube, but okay.
Why did you remember to cut that out?
I don't have time for that. Okay. I'm pretty sure he's not watching anyway. All right. So h decreases by a factor of, let's say, factor of k, let's say, k could be whatever. And the error is order h to the p for some p. So p equals 2 for trapezoidal midpoint and 4 for Simpsons. Does the error actually decrease by factor of k to the p? Now, if you look at, for example, f of x equals, say, e to the x, in that case, yes, that's generally what's going to happen. You really will see that kind of a decrease in the error. And actually pretty much anywhere, whatever interval. And if I look at square root of x as my integrand, and let's say on the interval 1 to 2, again the answer is going to be yes. But if I look at the interval 0 to 1, you'll find no. You don't get the decrease that you expect. So if you look at the error formulas, any of them, for any of these rules, why do you think that is? What makes the difference? So you look at what's involved in the error formulas over there, because what part of them could explain the difference in behavior? Okay, well, what is it about the derivative of square root of x? What is the derivative of square root of x? Yeah?
Well, that's first. Like,
Yeah, I know, I was about to say, I always just do it in the exponent form.
Yeah? Okay, good. So what of it?
Oh, 0 in your,
Yeah, that's exactly it. Because what's happening is, okay, the derivative is being evaluated at an unknown point. So you're not going to, and the unknown point is not going to be exactly 0. But as h decreases, that interval is getting smaller and smaller. Your unknown point from your first subintervals are getting closer and closer to 0. The derivative is getting larger, making the whole error term larger. Now, away from 0, those error terms are still going to be nice and small. But that first subinterval is going to kill you. So even though h is getting smaller and smaller, that derivative is getting larger and larger. And for a Simpsons rule, for instance, you're taking a fourth derivative. So it's getting even worse. So that's one thing to be careful about is how does the derivative behave? And I mentioned earlier, to get an error bound, you'd like to be able to bound the derivative on AB. And if you can't, then you got a problem. Okay. Oh. Diana was asking if we wanted to go watch tonight's debate, like on actual TV or something. We don't have TV at home. We don't have cable. We've got rid of cable 5 years ago. But
nice.
I'm also not sure if I can bear to watch.
Totally.
That's why you drink while you do it.
Oh, yeah, actually, yeah, in public.
Yeah. Did you see the game on Facebook?
No.
Oh man, they have a drinking game. Like every time Hillary lies or Trump.
Oh, I saw that.
Daughter.
Yeah. Actually, now that I think about it, yeah, in public could be really bad.
Yeah.
Here in Mississippi.
Oh yeah.
Oh gosh.
Okay.
I don't know if you hate them both equally.
I really don't want to hear what people have to say.
Yeah.
Yeah. Okay.
Yeah.
Good point.
Yeah, I don't think what the other people have to say.
That's a good point.
Anyone who hates both equally or is not paying attention.
Yeah.
So, okay, that's all I'm going to say about that. Oh, yes, I have an example. And it looks like okay, I still have 20 minutes left. Not sure I'm going to use that time. Okay, I'm almost done with this section at least. So I can definitely do that. Okay. looking at functions that talk about e to the x. I can show you one way in which these error formulas can be useful, is to determine how to choose h. So suppose our goal is to approximate this in such a way that your error is less than 10 to the minus 3. So at least you would get the 3 decimal places correct. And you want to choose n to be large enough. Because there's a trade-off. If you choose n too small, then you're going to sacrifice accuracy. If you choose n too large, you're sacrificing efficiency. So you want to have just enough subintervals and just large enough, and preferably no larger, to get the accuracy you want. Okay. So if we're using the composite trapezoidal rule, so our error, which we want to be less than 10 to the minus 3, so that's, we'll just take the absolute value. So minus f double prime, unknown point over 12, b minus a, h squared, is less than 10 to the minus 3. Okay, so now we can fill in all the particulars. So our function is e to the x. So second derivative is e to the x. So e to the eta over 12. And then a is 0 and b is 1. And therefore h, h is equal to b minus a over n. And that gets squared. So h is equal to 1 over n. So now I have this, e to the eta over 12n squared must be less than 10 to the minus 3. Now, for my e to the eta part, I want to make this as large as possible. I want the worst case. So eta can be anything between 0 and 1. So what should I choose it to make this as large as possible? So how can I choose eta? It could be somewhere between 0 and 1. How should I choose it to make this as large as possible for worst case? Yeah, because e is an increasing function. If it wasn't, then you'd have some work on your hands, to figure out the maximum and so forth. That'd be real pain. So that's less than or equal to minus e over 12n squared.
I have a question. E to the power x is an increasing function, but in compared to n squared, how I can...
Well, but right now we're treating n as a fixed parameter. Eta is variable.
Oh, that's different.
Yeah.
Okay.
Yeah, Greek letter eta versus regular letter n. Okay. Okay. All right, so now what I can do is solve this for n. So n must be greater than e over 12 times 10 minus 3 square root. Dang it. Okay. All right, so if I go ahead and work this out, it's roughly 15.1. So, well, n has to be an integer. So as long as I choose at least 16 subintervals, then we can guarantee that the error will be less than 10 to the minus 3. Although this is, because we made this as large as possible, chances are that would give us more than the accuracy we're looking for, but at least you know you'll get it. So any questions about how we did that? All right. 15 minutes left of suffering. I'm just so worn out. Which is not good because it's Monday, but okay. So that's Trapezoidal Rule. Similar thing for Simpsons. Okay. So the error in this case is minus e to the eta over 180 n to the fourth. Just filling in the particulars where it is a equals 0 and b equals 1 and all that. So that's less than or equal to e over 180 n to the fourth, which must be less than 10 to the minus 3. So now we can go ahead and solve this for n. So n must be greater than the fourth root of 1000 e over 180. But if we work that out, that's roughly 1.97. So n has to be greater than or equal to 2, which is funny because that's just basic Simpsons rule. We're not having to use composite Simpsons at all. But Simpsons, because Simpsons is that accurate, especially for e to the x, a nice smooth function, and on 0 to 1 it's not increasing that rapidly yet. And it's no surprise that you would need far fewer subintervals for Simpsons than for trapezoidal. In fact, we'll see an example later where, for a different function, to get 8 decimal places of accuracy, trapezoidal rule, you need 2,500 or so subintervals. And for Simpson's rule, you only need like 30-something. So it can be a big difference at 4/4 accuracy. So in fact, if I go ahead and use the basic Simpsons rule, now the exact value of this is e minus 1. So 1.7182818, etc. Now, the approximation I get is 1.71886. So I actually do get the first few decimal places correct. Okay. Any questions about that? Okay. Now, let's call on somebody. So, obviously not Haley, not Haley because he already went. So Stephanie,
Sure.
okay.
Which one?
Okay, so actually you pick any of the problems from chapter 1 that Haley did not do.
Okay. Well, the one I have them all. The one I most recently did was 9, but it's like super long. Do you want me to write all of it, or do you want me to just like explain it and write pieces?
Well, I guess
Can you see it?
maybe only
See, it's
there'd be a little more detail on the first one, like to
like maybe
how to
show
get
the
that.
first few and explain how to get the rest of them.
Yeah, and you don't have to do like all algebraic steps, but like the most important thing is, since you're having to neglect terms of order epsilon squared,
Right.
like show that. But,
Okay.
Yeah.
Perfect. Grab my book. Okay. Does everybody like have everything they need? Good. Good job.
Oh.
That's good job. There we go. Okay. Number 9 said, the secant method is used to determine solutions of the equation x squared minus 1 equals 0. And then, so you have, and then they gave you they gave you they gave you 2 initial values. Okay, and the first thing that you had to do was prove that x2 equals 1/2 epsilon okay, here we go. So secant method is x sub k plus 1 equals x sub k minus f of x sub k times x sub k minus x sub k minus 1 over f of x sub k minus f of x sub k minus 1. So basically you're just going to take your 2 initial values and plug them into here and do a whole bunch of complicated algebra. So I'm going to do like every other step or something like that because it's from here to here. So I'm just going to do a few. So to find x2, we would have x1 minus f of x1 times x1 minus x0 over f of x1 minus f of x0, which if this is our equation, then our f of x is going to be x squared minus 1, right? So I'll write the first. We have -1 plus epsilon minus, let's get that step, -1 plus epsilon squared minus 1 times -1 plus epsilon minus 1 minus epsilon over -1 plus epsilon squared minus 1 minus 1 plus epsilon squared minus 1. Okay. Good so far? I feel like I'm teaching my geometry class. Do you have any questions? I know? Okay, good. They always have questions. All right, so I'm going to let you do all of the complicated algebra. But basically, you do a whole bunch of algebra and it gets you to -1 plus epsilon plus 2 epsilon squared minus 4 epsilon over -4 epsilon. So when I was doing it, I got to this step really easily and then it took me a while. But you basically have to write it as 2 separate terms with obviously the denominator under each one. Okay, so this was all our initial info. Okay, so you get -1 plus epsilon minus 2 epsilon squared over 4 epsilon plus 4 epsilon over 4 epsilon, which is -1 plus epsilon minus epsilon over 2 plus 1, which is of course 1/2 epsilon. Okay. So you do all that to prove that x2 equals 1/2 epsilon. And then they want you to find x3, x4, and x5 the same way. So it takes a really long time. And then you have to prove that it all converges to -1. So I'm going to do x3 for you because you kind of have to do a little trick at the end. It's really fun. Super fun. Am I okay on time? Yeah. So good. Okay. All right, so for x3, you're doing x2 minus f of x2, x2 minus x1 over right, and that initially gives you 1/2 epsilon minus okay. So all I did was plug x2 and x1 in using this as my function and secant method, right? So I'll save you the boredom of all of the algebra. And 3 pages later, we are at, all the way at the bottom. Okay. So eventually you get this. -1 plus epsilon squared plus 2 epsilon over 3 epsilon minus 2, right? And you can factor an epsilon out of the numerator. Right? Okay. And this term that's in front of the epsilon that you pulled out is basically a constant. So to determine what this constant is, you let the epsilon in this portion be 0. Okay, so if you did 0 plus 2 over 3 times 0 minus 2, you'd have 2 over -2, which is -1. So you have -1 minus epsilon. And that's basically like the process that you use, letting it be 0, to neglect higher order terms. Did I explain that right?
Yeah, and so
Okay.
and that was continued with x4 and x5.
Yes. So you do x4 and x5 literally the exact same way, and in every single one you have to factor an epsilon out at the end, and then let this portion be 0. So you end up getting that x4 is -1 plus epsilon, and let's see. Yeah. And x5 is -1. Mm-hmm.
Okay, so anything else is like order epsilon squared or worse.
Right.
Okay.
And actually, after you get, so the next part was that you had to prove that it was converging to -1. So I just found like x6 and x7, and they're all exactly -1.
Yeah.
Like once you get -1 and you start plugging it in, that's all you get, and it's the easiest way to prove it. And then you have to do everything again with x0 and x1 switched, and it's the exact same process. You just do the whole thing again, and then that time it converges to 1 rather than -1. But you can prove it the same way. Like if you find x5, x6, and x7, you'll get 1 over and over again.
Alrighty.
Okay.
You see the problem.
Question, when you got that part right there, when you said it equal to,
0.
okay.
Yeah. Mm-hmm. So this epsilon stays, and then this portion becomes a constant, so you let epsilon be 0 just in this portion. So you ended up getting like -1 times epsilon or minus epsilon.
Alright.
Okay.
Now, I guess what basically what you're doing is you're demonstrating that the value is getting closer and closer to -1. When it really
Yes.
comes to the proof per se, I know. So I guess the way you go about proving it is similar to other error analysis that we've seen, except in this case you have a specific function to fill in, where if you look at the error like xk plus 1 minus a minus 1, like you subtract minus 1 from both sides and see what happens to the error. And if you make the assumption that xk and xk minus 1 are already sufficiently close to that minus 1, like differing by epsilon or something, then yes, the error really will get smaller. Because what you're doing is you're sampling and saying, well, that looks like it's going that way, but yeah. So actually, that would be a helpful exercise to do that.
Perfect.
Yeah.
I'll add that to the 6 pages of number 9 that I already have.
Yeah. That's graphical.
Yeah.
Now, the way you figure out what this constant is, because they only want expansion up to through the term order epsilon. So more generally, if you have some function that depends on epsilon and you want to figure out like a low order approximation, the general way to do it would be like f of 0, just a Taylor expansion around 0. And if you needed higher order terms, you would use higher order derivatives. What I was showing you for this basically accomplishes this. So at least the algebra worked out nicely enough. You can say, oh, where's that epsilon? And when you plug in epsilon equals 0 to the rest, you're basically you're figuring out what f prime of 0 is. Yeah. So, but more generally, and it's also illuminating to look at this from a graphical point of view. If you were to graph x squared minus 1 really carefully, and also draw your iterates very carefully. So in this case, 1 plus epsilon, and 1, or no, minus 1 plus epsilon also. So your starting function values would be here and here, and you draw that secant line. And I think I didn't draw it carefully enough. But yeah, so it's the intersection is going to be near 0, but really it's supposed to be epsilon over 2. And yeah, I did not draw this carefully enough. But then, if you're around here, and you draw, okay, so now you go down here, and you draw this secant line. See, now it goes the other way, and brings it back to minus 1. But now, what you're doing is, okay, so this is x1, x0, x2, x1, x2 give you x3, and now when you do this secant line, it's between this point and this point, which keeps you around minus 1. So depending on how carefully you draw your graph, you get an idea as to what sort of iterates you're supposed to get to kind of act as a check on your algebra. But again, it takes a real careful graph, which I didn't do. So, okay. Oh, well, we're out of time. So, alrighty. So, only 6 victims left.